Hey, Unit 2, Part 2. You know you're excited to learn this one, okay? Inverse functions and identities. All right? You would think this wouldn't be as difficult as it was, but a lot of you were either started to get sick, that was the change of the seasons, and you missed several days. So we really want to make sure you've practiced this, you know this, you can apply everything that we've taught you with everything that we have done so far. Math is a continuation. You need to make sure you can build on it. Okay, so inverse functions and identities. That was it. Let's get started. Inverses, all right? Ordered pairs, you switch your x and y values. In an ordered pair, you switch your x and y values, and that's the inverse. Don't overthink it. Don't make it extra complicated. Just use logic. Switch your x and y. Now, where it gets tricky is when we're talking about domain and range, okay? When you switch your domain and range, you do not change the order of your domain and range. You don't change the ordered pair, okay? I should say the ordered pair of your domain and range. Don't change that. Don't change that ordered pair, okay? It won't work. It doesn't work like that. This domain, this function right here, as I move to the next slide, this function right here, or not function, this domain, this ordered pair right there would represent your entire x. And this range represents your entire y, okay? So we don't mess around with that order, okay? You're going to invalidate your function. It just doesn't work, right? So that is why we simply take this range and we put it for our domain, and then the domain for your range. We don't mess around with the order. Notice your inverse domain is negative infinity to positive infinity. I didn't make it go from positive infinity to negative infinity. That wouldn't make sense. We don't read a graph like that. It does not make sense, okay? And then our range is 4 to positive infinity. Again, we would not say positive infinity to 4. It doesn't make sense. Think about it logically. Don't sit there and scratch your head. Don't think harder, think smarter, okay? You can do this. After that, we talked about a graph. What do we do? How do we identify the inverse of a graph? Well, we have this y equals x line, this diagonal line that crosses through the origin that has a slope of 1. That line right there, if it's symmetric about that line, if you can literally fold that corner, this corner right here down, and your graph matches it, it is an inverse, excuse me. It is an inverse. Don't overcomplicate it. If you need to, all you got to do is plot that ordered pair. That ordered pair is that negative 1, 1. Well, what's the inverse of that ordered pair? 1, negative 1. So we'd go to here, down right there, okay? That works. So you can use ordered pairs to check as well. All right, use several, okay, if you can identify a couple, use a couple to make sure that it is truly an inverse. You can always fall back on that. Think smarter, not harder. All right, that's inverses. Algebraically, that's a different story. The same approach applies. Switch your x and your y, okay? In this first example, right here, in example number 1, right there, you are going to simply switch your x and y's, okay? They did it in red, all right? If you're watching the video, you see it. You probably won't see it if you are just looking at the PowerPoint, all right? So maybe get a red and blue highlighter and highlight those colors on your paper, all right? Or whatever you need, just highlight that. You switch your x and y's, and then you solve for y, all right? So as you go through this example, you can see where they did. They moved the constant over by adding 5 to both sides. This became a 0. X plus 5 equals 3y. Well, we're not finished. We need to now divide by 3, okay? Because that's your coefficient of y. We need to divide by 3 on both sides, and that gets you x plus 5 over 3 equals y. We're not finished. You have to write it in proper function notation, okay? Since we found the inverse, we write f of negative 1 of x equals x plus 5 over 3. Okay. Another example is given to you over here. This is my second example. Okay. Y equals x minus 2 squared plus 4. We can't do anything with this x minus 2 squared until we get rid of our constant. By getting rid of it, move it to the other side, okay? So we're going to subtract 4 from both sides, x minus 4. And then at this point, we take the square root of both sides. This becomes 1, all right? This becomes plus or minus the square root of x minus 4. When we have an even function like that even square root, okay, we have to do the plus or minus, all right? Some of you forgot to do that on your test. Now, at this point, we can add 2 to both sides. This does not, I repeat, does not become x minus 2. It is not a like term. You cannot do that. It's not worth it. Don't do it. Don't waste your time. It is a completely different term. So you would put it outside the radical symbol. Notice that radical symbol, that square root symbol, does not extend to that positive 2. Okay? It doesn't extend. Don't do it. All right? So now you rewrite it in function notation. If you need to do the symmetric property, the inverse of x, f to the negative 1 of x equals plus or minus the square root of x minus 4 plus 2. Now, boop, that is what we need. Okay? Any questions, please ask your teacher. Next slide. After we did the inverse algebraically, we asked you to verify, okay, to verify inverse functions through composition, okay? We know you loved composition so much, we just wanted to show you what cool things it could do. And this is actually very neat, okay? You can always check to check yourself and see if you really did find the inverse by plugging in, using function composition, using function composition to figure out if they're right. What does it always equal? When you're doing function composition, right here, ladies and gentlemen, both functions must always equal, when you do the composition of them, must always equal x, okay? And if you remember, when we're verifying, you have to do both directions, part 1 and part 2. If we're looking at this example right here, this is part 1 and this is part 2. You have to do the 2 different parts. You have to go both directions. The first direction is most direct, f of g of x. G of x becomes your new x. So 2 parentheses 1/2 x minus 2 close parentheses plus 4. Distribute the 2. Don't be afraid of the fractions. Do not be afraid of fractions. You have a calculator. Use your calculator. Don't give up and say it's too hard because it's a fraction. No, use your calculator. Okay? When we distribute, you'll get 2 times 1/2 is a 1x. And then 2 times 2 is of negative 4. So x minus 4 plus 4, combine like terms, x. So this one checks out. Now, part 1 works. Let's check to see if part 2 works. 1/2 x. Okay, we're now looking at this right here, going into this function as its new x. 1/2, parentheses, 2x plus 4, close parentheses, minus 2. Distribute the 1/2. 1/2 times 2 is 2 over 2, which gives you 1x. 4 times 1/2 is going to give you 4 divided by 2. 4 divided by 2 is 2. X plus 2 minus 2. That crosses out, giving you a 0. So this works. So these are inverses of each other. Okay. Here's another one for good measure. Please work through these and make sure that you know how to do this. If you are confused, please ask your teacher and we will give you more practice. The last part of this unit is identities. We are giving you the identity sheet on your final exam. We gave you the identity sheet when you took your first test, okay? I'm still a little peeved about this. I apologize, okay? What identities are, ladies and gentlemen, is application. You have to know how to apply these identities, okay? It's just a matter of plugging in. It's like me giving you a formula and saying, can you figure it out? You all can do the quadratic formula. In fact, you want to do it all the time. So this has the same thought process. Can you apply your A and B? Can you use what knowledge they give you, what information they give to you? Can you use that and apply the following identities? Okay? So let me go through these real quick. The first one, the difference of squares. They're going to give you an example like such. Okay? It doesn't have to be a perfect square. We want it to be a perfect square because then it's all pretty and nice, but sometimes it's not, and you're going to have to get over it. So, an example of this one would be 4x squared minus 11, okay? And again, we're giving you this and we're asking you to use one of the identities to simplify it. So right off the bat, you need to pick one and use it. Now, I'm going to just go in order. So, difference of squares. It tells you that you can take the square root of A and the square root of B and give you the simplified version. Add one term and subtract the next one. So, the square root of 4x squared is 2x. Did you know that? I hope so. All right. And then, since it's a minus sign, one will be a plus and one's minus. Does it matter, Miss Smith? No, it does not matter which one you write it as. It really doesn't. Just identify and be able to understand that those are fluid as well. They're flexible. It goes both ways. Now, we have to take the square root of our B term. Is 11 a perfect square? If you said yes, it's not. Okay, put in your calculator, you get a decimal. The square root of 11, can it be simplified? No, it's a prime number, so I'm simply going to leave it as the square root of 11. Nothing fancy, nothing crazy, just leave it as the square root of 11, all right? And that is the difference of two squares, all right? Is it perfect? No, it is not perfect because it's not a square. 11 is not a perfect square. But for the sake of application and for the sake of test-taking skills, if they ask you to use an identity to take or simplify this, expand or go the other direction, that is what you would do, okay? Think smarter, not harder. The next one, okay? My personal favorite, the sum of squares. It is very easy to identify because there is an I. Now, I'm not going to explain why this works, but all you have to do is use the area model to figure out if you are correct. And what you will see is that yes, using the area model or FOIL, it will give you this sum of squares. All right. Now, I am going to do nice numbers because I like nice numbers. So I'm going to do 16x squared plus 36. Now, because this is plus, it's the sum of squares, and you would just take the square root of both. The square root of 16x squared is 4x, okay, plus 36. What's the square root of 36? That is 6, but since it's sum, we have to add in the I. And then we need to write it again with a minus sign. Application, ladies and gentlemen, application. All right. The next one's the sum of two cubes and the difference of two cubes. How do we identify this? Well, there's a plus sign, so it's going to be a plus sign here. The difference, there's a minus sign between these two cubes, okay? So there's going to be a minus sign in between those. That is the way you can quickly identify which one is which. Now, the one thing I'm going to say about this is on your calculator, you can press math and then go down to 4 or 5, that section, and that will give you the cubed root button. This one will give you where you can type in your own degree, okay? I don't care which one you use. It just depends on what your teacher told you. All you have to do is take the cubed root of whatever numbers they give you and then just put it in place. All right? Perfect square trinomial and binomial squared and binomial cubed, both of those are Pascal's triangle. So if you knew how to use the binomial theorem and Pascal's triangle, then these two right here should not have been a problem. Now, that matching portion on that test, if you remember, what you could have done is literally counted how many terms were in place. This is a plus b squared. There are 3 terms right there, ladies and gentlemen. So that quickly matches to the only one was there, okay? There was only one choice that had 3 terms. And then for this binomial cubed, there's 4 terms. There was only one answer choice with 4 terms. Only one. So there was no excuse for you getting that wrong, okay? If I'm offending somebody's feelings, I apologize. It's just one of those things, all right? You guys can do this. It's about application, all right? If you need help with that, please come and ask us and we can go through it. I know I have several notes on this that I've handwritten myself that I have put on my Aspen page that I can easily forward out if you need them. So, any questions? Let me know. After this, we get into the binomial theorem and Pascal's triangle. The binomial theorem and Pascal's triangle tells you that we can have a shortcut instead of doing these little boxes over and over again. Doing these boxes, this one, and then we got to do this one, whoop whoop, and then we got to do we go up 1 to the 3rd, and then that. I mean, it's just excessive, okay? The amount of work just becomes excessive. We were able to use this binomial theorem and Pascal's triangle to find a beautiful pattern, okay? An awesome pattern that helped us simplify it. This right here, this example was given to you in your packet, and there are several good examples in your packet that you can refer back to. And if you just need practice, that is what it is. The big thing you need to notice is as your A term, you see these exponents right here, 4, 3, 2, 1, 0, as that decreases, your B exponents increase, okay? They will always add up to whatever degree you have here. So 4 plus 0 is 4, 3 plus 1 is 4, 2 plus 2 is 4, 1 plus 3 is 4, and then 0 plus 4 is 4. They always have to add up. Everything has to make sense. It is logical, it is beautiful, and it's real. Okay, you guys? I love this type of math. All right? If you have questions on that, it is very easy for me to sit down and explain it to you, my students, or go ask your teacher, okay? Go see what you're missing, work through an example, go online, YouTube it, find another video that explains it. It just takes a little bit of time, all right? If you have any questions, please come see me. Extra practice. I'm sure you did not do all of it in the packet. You can go back to your packet. If you've lost your packet because you're unorganized like myself, you can go to your teacher, and I'm sure they have practice pages on their computer that they can quickly print for you. All right. Any questions? Hope not. There we go. There we go. I'm going to